Question?
Were we going to go over last week's, the end of last week's answer? No. I could not remember. I couldn't remember if you said you were just going to go.
Oh yeah, there was something that I said I would go over if there is demand.
Okay.
I think. Right, so there was this false implication. So we had this condition that says that L is the limit superior if and only if some stuff happens. And I think we proved last time that if L is the limit superior, then these two conditions hold. You guys take some time in the past 48 hours and think about why the contour should happen? I guess a better question is, should I talk about why the converse is true? I will talk about why the converse is true. Cool. So let's remember what the theorem even said. So the theorem was, for a bounded sequence A sub n, a number L is the limit superior of A sub n if and only if for every epsilon bigger than 0 and every m and n there exists some little n bigger than big N such that absolute value of A sub n minus L is less than epsilon, which we had established earlier, this pink box is equivalent to L being a subsequential limit. And a second thing also has to happen. For every epsilon bigger than 0, there exists a big N such that for a little n bigger than big N, A sub n is less than L plus epsilon. So eventually, A sub n isn't much more than the the limit superior. Let's do it then. Let's suppose that a number L satisfies these two conditions. And let's show that this number L is the supremum of the set of all subsequential limits. There are two things I'll do. I'll show that L is an upper bound and that L is a subsequential limit. Does someone just see why one of those should be true automatically? Which one do you see?
L being an upper bound on the blackboard, full L.
Why should that follow? Okay, well, maybe I'll talk. So let's say the intuitive reason. If I take a convergent subsequence, then there's a bunch of n sub k's. Eventually, will those n sub k's exceed this big N? Yeah, because the n sub k's have to go really big. So then A sub n sub k will satisfy this condition. So what can you tell me about the limit of A sub n sub k? Less than or equal, well, L plus epsilon.
Yeah.
But then since that's true for every epsilon, it has to be less than or equal to L by a theorem that you guys proved a while ago, like day 1 of class. So let's do that. And maybe I'll come back and fill in those blanks in a moment. So let's show that L is an upper bound. So how do you show something's an upper bound? Right, let's get all the formatting correctly. To be an upper bound, you have to be bigger than or equal to everything in the set. So let's consider an arbitrary anything in the set. Let's let A be in blackboard bold L. So it's a subsequential limit of A sub n. We need to prove something. I'm going to fix any epsilon bigger than 0. So there's a subsequence A sub n sub k which converges to this A because it's a subsequential limit. So by this second assumption, there exists some big N such that for all little n bigger than big N, A sub n is less than L plus epsilon. And now I'm going to say in more words the same sketch as we just stated. As soon as little k is bigger than big N, then n sub k is bigger than or equal to k. Hey, look, we're using that claim that n sub k is always bigger than or equal to k again for any strictly increasing sequence of natural numbers. Is bigger than big N. But as soon as n sub k is bigger than big N, we can use this claim. We can use this fact. So that a sub n sub k is less than L plus epsilon. So I know that for all little k bigger than that big N, a sub n sub k is less than L plus epsilon. Does that mean the limit should be less than L plus epsilon? We see that the limit of a sub n sub k is less than or equal to L plus epsilon. Since this is true for any epsilon, we can now conclude that the limit of a sub n sub k, well, that's exactly what we called a before, is less than or equal to L. We've just concluded that absolutely every element of blackboard bold L is less than or equal to L, so L is an upper bound on big L.
You don't get the or equal to until you take out the epsilon, though, right?
Ah, you do it as soon as you take the limit. So remember this example?
Oh, yeah.
Right, like 1 over n is bigger than 0 for all n.
Yep.
So even when you take the limit, you're going to lose straightness.
Got it.
I guess kind of de facto, since we know that A is really actually less than or equal to 12, we do know that we have strict inequality there. But if we assume that right now, it would feel pretty solvable. Nice. So that verifies that L is an upper, the number L is an upper bound on the set blackboard bold L. That was one of the two things we wanted. We also said we were going to show that big L is actually a subsequential limit. Let's do that. Did I actually not leave space? Ah, okay, no, there's space right here. So I'm going to, just for the sake of consistency, box this in pink because it was boxed in pink on the previous page. What is that condition equivalent to? By lemma 2.5.7.
L being a subsequential limit.
Yeah. So since we assume those two things are true, so I guess we did it like out of order and all over the place. But at this point, have we actually checked those two conditions? So we know that L is an upper bound on the set and L is an element of the set. So that should mean that L is honestly the biggest thing in the set, because it's in the set and there's nothing in the set that's bigger than it because it's an upper bound. So it's actually the maximum element. But does that also mean L is the supremum of the set? Should we talk through the formality of why? Okay, let's do it. So let's see why this will complete the proof. So what does it mean to be the supremum? It needs to be an upper bound. Is L an upper bound? L is an upper bound on L by 2. What is the other thing you need to be true for L to be the supremum?
It needs to be in the set.
Well, we know it's in the set, but that's not part of the definition of the supremum.
All upper bounds have to be less than or equal to, greater than or equal to.
Yeah.
L.
It needs to be the least upper bound. Every other upper bound needs to be bigger than or equal to it. So let's consider any upper bound U on L. Why should it follow that U is bigger than or equal to L?
Sorry, can you like tilt it?
Oh, yeah. Yeah, sorry, I can't see the screen at all from where I'm standing. So it's hard for me to gauge when bad things happen. It's actually on screen now?
Yeah.
Okay. Let's see, is the number L an element of blackboard bold L? Is U an upper bound on blackboard bold L? What inequality can you deduce?
Use greater than
U is greater than, oh, well, R equals 2.
Yeah.
So, as L is in L by 1, by 2, and U is an upper bound, we see that U is bigger than or equal to L. Thus, L is equal to the supremum of blackboard bold L, which is exactly the definition of lim sup of A sub n. Nice. That was a little bit out of order, but did the steps make sense? Cool. People have any questions before I go back to the concept of Cauchy sequences? Okay, cool. All right, so Cauchy sequences. So right now we have this fairly general theorem that says that as soon as you know that a sequence is monotone and bounded above, it follows that that sequence converges. And that's what's called a sufficient condition for convergence, because you know that if a sequence satisfies the condition of boundedness and monotone, then the sequence converges. And we use that to get some mileage. We use to prove that some series converges. Do you think that's an if and only if? Is a sequence convergent if and only if it's monotone and bounded? Can you think of a non-monotone sequence that converges? Yeah, if you can't cook up a formula, of course you can just like have something that wiggles up and down and still gets close to something. I guess the prototype is -1 to the n divided by n. It's not monotone, but it converges. I'm going to actually get an if and only if here, something that's equivalent to saying that the limit exists without making a reference to what the limit is. And that condition will be the Cauchy criterion. So here's a definition. A sequence A sub n is called a Cauchy sequence if for every positive number epsilon, there exists some big N such that whenever m is bigger than big N and n is bigger than big N, then the absolute value of A sub n minus A sub m is less than epsilon. So I guess let's say that informally. That says that no matter how close you want the terms of the sequence to be to each other, they are that close to each other as long as you look far enough in the future. So that's kind of like the statement of convergence, except there's no reference to what the limit is. So here is, so there's the idea. So the main goal of this note packet, which I think we can make it through even in a shortened time, is this theorem. A sequence is convergent if and only if that sequence is Cauchy. And an example which I think I will put off till the end and then I'll come back to is the following application. Here's a sequence. S sub n equal to the sum from k equals 0 to n of -1 to the k divided by 2 to the k plus 1. There's a sequence. That certainly gives you instructions for how to construct a number for any fixed n. I claim that that sequence is Cauchy. And I think that I'll put off the proof of the claim that it's Cauchy. But as soon as you know it's Cauchy, that sequence converges. Here's something that's important. I have no idea what the limit of that sequence is. This hasn't told me what the limit is. So there's no way I have any hope of coming up with an epsilon n proof that the sequence converges. I don't even have a guess for what the limit is, so I wouldn't be able to even set up an equation like A sub n minus L is less than epsilon. I don't know what L is. So I'm going to skip all this analysis. We'll come back to it at the end quickly. Maybe I'll just say for now, if you want to know what the limit is about, well, you can plug in n equal to like 1,000 and find out that the limit's probably pretty close to -0.2057. But chances are that whatever number this limit is, I don't even have a name for it. Right? Somehow I also only have like finitely many names I can give numbers. So there's like a 0% chance this is one of those. So this is actually, this gives you a technique for checking that something converges without having to have a guess for the limit. And one thing that's useful is once you know that something converges, you can say things about the limit without being circular. You can say, I know it converges. By plugging in a really big number, I know that the limit is pretty close to this. People feel okay? We'll come back to this actual computation. I want to, however, get through the proof. So let's prove that a sequence is convergent if and only if that sequence is Cauchy. Well, it's an if and only if, right? So let's try to prove it. And I'll do the easy and not interesting direction first. If a sequence converges, then that sequence is Cauchy. And maybe we'll even just try to draw a picture of it. So let's let a sub n be a convergent sequence. Let's suppose that the limit of a sub n is some number a. I need to show that for every epsilon bigger than 0, there is a big N such that for every m bigger than big N and every n bigger than big N, absolute value of a sub n minus a sub m is less than epsilon. And here's how I'll draw a picture of the proof. I'll draw a little dot representing a sub n. I'll draw a little dot representing a sub m. I want this to be less than epsilon by taking little n and little n big enough. But by taking little n to be big enough, what could I get a sub n to be close to? The limit which, did I call it L or did I call it A? A, okay. So I can get this, if there is A, I can get this distance to be as small as I want by taking little n to be really, really big. Could I get the distance from little a to little a sub m to be really, really small? Yeah, right, by the exact same argument. When little m is big, then a sub m minus a is less than epsilon. So I can get this to be really, really small. Well, let's check it out. The distance from there to there, well, if that's epsilon, and the distance from there to there is epsilon, then that means that this bottom distance by the triangle inequality is less than 2 times epsilon. Is that good enough? It's not. I need it to be less than epsilon. So what trick do you think that I'll use?
Epsilon over 2.
I'll use like the epsilon over 2 trick. By taking little n to be big enough, can I get that side to be less than epsilon over 2? By taking little m big enough, similarly, I can get that to be less than epsilon over 2. Now that bottom side will be less than epsilon. And now I even know how the proof is going to go by the way that I thought while drawing the picture. So this picture isn't part of the proof, but it tells me how I'm going to write the proof. So there's the pausing here to draw a picture. So here's the game. We'll consider any epsilon bigger than 0, because we must. Did I already? Yeah, because I need to show something for every epsilon, so I better consider any epsilon bigger than 0. Let's see, since a sub n converges to a, there is a big N such that whenever little n is bigger than big N, then the difference between a sub n minus a can be as small as we want. And how small did we just decide that we wanted? Epsilon over 2. I've just come up with a choice of big N. The Cauchy criterion says, well, sequence is Cauchy if for every epsilon bigger than 0, there exists a big N such that for every little n bigger than big N and every little n bigger than big N, absolute value of a sub n minus a sub m is less than epsilon. So I need to prove something is true whenever little m is big and little n is big. Let's consider any little m and little n and assume that those two inequalities. Let's see, since little n is bigger than big N, what can you tell me about a sub n minus a? Less than epsilon over 2. What can you tell me about a sub m minus a? Less than epsilon over 2. And now I'm going to use like the standard triangle inequality trick. I know that they're both close to a, so I'll subtract and add a to find that the absolute value of a sub n minus a sub m, which I want to be very, very small, is the same thing as a sub n minus a plus a minus a sub m is less than or equal to the absolute value of a sub n minus a plus the absolute value of a minus a sub m. But do I have an upper bound on the absolute value of a sub n minus a? Yeah, what upper bound do I have? Epsilon over 2. And it's even like a strict upper bound. Do I have an upper bound on the absolute value of a minus a sub m? Yeah, because the order that you subtract things doesn't matter inside an absolute value bar.
Is there a name for that property?
Which one?
That it doesn't matter which way you subtract things at an absolute value bar.
I guess you could call it symmetry.
Okay. Because I've used it in multiple proofs, and I kind of end up just writing like by absolute value subtraction.
Yeah, so I guess what is really being used there is I'm going to wax slightly more abstract. You could do all of this analysis stuff in any place where you can measure the distance between things. Because absolute value just gives you a way of measuring distance.
Right.
And distance, any reasonable distance function should have a symmetry property. Distance from here to there is the same as distance from here to here. So that's what I mean by this symmetry.
Okay. So you could call it like absolute distance, if that's a thing.
Sure. I mean, you could just say symmetry of distance.
Sure.
Or even just m minus a by. If you say that, I'll know what you mean.
That's a bit off the page, but
That's okay. I went by symmetry.
okay.
Nice. So let's check that this actually proves convergence. Did at some point in the proof I consider any epsilon bigger than 0? Did I conjure up a choice of big N? Yeah, it was boop-a-doop-a-doop-a-doo. So there I considered any epsilon bigger than 0. I came up with a choice of big N. Of course, I couldn't say explicitly what big N is because I don't have a formula for a sub n. I had to use the assumptions given to get the big N. Did I consider absolutely any little m and little n bigger than big N? Did I then prove that absolute value of a sub n minus a sub m is less than epsilon? It's Cauchy. How do people feel about that? That seem okay? Nice. So that's like kind of a silly direction to go, because the limit existing means everything is getting close to a single number. I just proved that if all the terms of the sequence get close to a single number, then the terms of the sequence get close to each other, but of course they do. That's not surprising. I need to prove that if the terms of the sequence get close to each other, then there's a single number that they're all getting close to. Which is maybe also not surprising, but is going to actually use some of the properties of the real numbers. Let's prove that Cauchy implies convergence. So let's suppose that a sub n is a Cauchy sequence. Here's the way the proof will go. First, I'm going to find a candidate to even be the limit. And here's what I'll do. Let's see, if the limit existed, then it would also be the same as the limit of all of the subsequences. So if I can find a subsequence which converges, then I can grab the limit of that subsequence and I'll have a candidate. And it'll be the only possible option to be the limit. If it's not the limit, then there is no limit. So for step 1, I'll find a convergent subsequence. I'll take the limit of that subsequence and prove that that is the honest-to-God limit of the whole sequence. When do sequences have convergent subsequences? When they're bounded by Bolzano-Weierstrass stress. So I will prove that every Cauchy sequence is bounded. Which seems like boundedness is such a floppy property that it should be easy. So let's suppose that a sub n is Cauchy. I'm going to find a candidate to be the limit. Step 1, I'm going to prove that this sequence is bounded. And this is something that we've done before when we proved that every convergent sequence is bounded. I said, well, boundedness is super floppy, so I can just pick an epsilon and it'll probably prove something. Let's take epsilon equal to 1. If you would rather rewrite this with epsilon equal to 5 or a half, go for it. It won't matter. This happens to be my favorite positive number. So there exists a choice of big N, such that if little n and little m are bigger than big N, then absolute value of a sub n minus a sub m is less than epsilon, which right now happens to be 1. All right, so I just used the definition of Cauchy with a single choice of epsilon. Cauchy means I know something about absolutely every positive epsilon. 1 is a positive epsilon. So here's what I'll do. I'll take little m above to be big N plus 1, and consider any little n bigger than big N. Do I right now satisfy that little m and little n are bigger than big N? Yeah. So I conclude that the absolute value of a sub n minus a sub big N plus 1 is less than 1. Do you think I could massage that inequality around and get bounds on a sub little n? Yeah, sure can. And it's something that we've done before. So we wind up with -1 must be less than a sub little n minus a sub big N plus 1 is less than 1. So a sub big N plus 1 minus 1 is less than a sub little n is less than a sub big N plus 1 plus 1. Have I just found an upper bound on the sequence? And a lower bound? Yeah, well, I mean, basically. That only happens as long as little n is big enough. So we have bounds on the set of all things that look like an as long as little n is bigger than big N. But maybe I'll say words about, because we've gotten something like that before, right? So we've proved that it's bounded as soon as little n is bigger than big N. How many natural numbers are there that are less than or equal to big N? Finitely many. It might be big N or big N plus or minus 1. I probably have an off by 1 error in my head. But I don't care. They're only finitely many. So there are only finitely many a sub n's with little n less than big N. Are finite sets bounded? Yeah. Do you think you could use that information to assemble an actual upper bound for every choice of little n? And we've actually done that before. See a proof from the limit laws packet for the resolution of this, namely the one where we prove that convergent sequences are bounded. I think that I would rather have you guys read through that and figure out the details than do it myself. Okay, cool. So this sequence A sub n is bounded. What does Bolzano-Weierstrass say about every bounded sequence? There is a convergent subsequence. So A sub n has a convergent subsequence. And I guess more specifically, it has a subsequential limit. Let's let A be a subsequential limit of A sub n, and A sub n sub k be a subsequence of A sub n, which converges to A. So now, if A is a subsequential limit of A sub n, what is the only possible place A sub n could converge to? A. Because the subsequence converges to A. That's the only candidate to be the limit. Let's prove that it's the actual honest-to-God limit. Let's prove that A sub n converges to A. All right, cool. So let's put the things we know down right now. I know A sub given A sub n sub k converges to A, and A sub n is Cauchy. Those are the things I know. So let's just try to unravel definitions. Well, I guess we need to prove a limiting claim, so let's consider any epsilon bigger than 0. So let's see, since the sequence A sub n happens to be Cauchy, there exists some big N I'll call it big N1 because I'll get a big N2 out of this line, such that as soon as little n is bigger than big N, little n and little m whenever things are bigger than this quantity big N1, I get a sub n minus a sub m less than epsilon. I might wind up having to divide that by 2, but I'll come back and retroactively fix it once I know what I need to divide it by. If you have a guess already, maybe you can divide it by 2 and see if that'll be good enough. I don't think it will. So that's just unraveling what it means to be Cauchy. I also know that a sub n sub k converges to a. So there exists some quantity big K such that if little k is bigger than big K, then a sub n sub k minus a is also less than epsilon. Oops. Nice. So let's consider the following. Let's consider a choice of little k such that little k is bigger than big K and n sub k is bigger than the thing that I called big N sub 1. Let's see, is it obvious that such a number k exists? Can I eventually make n sub k as big as I want, while at the same time making little k as big as I want? Yeah, of course I can. For that choice of k, and any little n bigger than big N1, I have, let's see, do I have an upper bound on what a sub n minus a sub n sub k is? By something on the bottom of the previous page? Yeah. Yeah, right? N and n sub k are both bigger than big N1. So this quantity is less than epsilon. Maybe that's what. Since little n is bigger than big N1, and n sub k is bigger than big N1. Do I have an upper bound on how big a sub n sub k minus a might be?
Epsilon.
Also less than epsilon. And that's just because little k is bigger than big K. All right, so let's see. A sub n is now close to a sub n sub k, and a sub n sub k is close to a. Does it follow then that a sub n is close to a? Yeah. I mean, I guess it's like twice as far away, so maybe I need to divide some things by 2. Let's do that first. So I'm going to use the same triangle inequality trick. I know that a sub n and a are both close to this quantity, so I will add and subtract that quantity. A sub n minus a is the same thing as a sub n minus a sub n sub k, plus a sub n sub k minus a, is less than or equal to absolute value of a sub n minus a sub n sub k, plus the absolute value of a sub n sub k minus a. Do I have an upper bound on how big a sub n minus a sub n sub k is? It's less than epsilon. Do I have an upper bound on how big a sub n sub k minus a is? Epsilon. Do those two things add up to epsilon? No. So what do I need to do? Divide by 2. So let's divide some epsilons by 2. So we consider any epsilon bigger than 0. Since a sub n is Cauchy, there is a big N1 such that for all little n bigger than big N1 and all little n bigger than big N1, a sub n minus a sub m is less than epsilon in Cauchy. And maybe we'll even check our proof as we do that. Is that actually true? Can I make a sub n minus a sub m less than any fixed positive number? Yeah. Epsilon over 2 is a positive number. Let's use that. Does there exist a big K such that as soon as little k is bigger than big K, this is less than epsilon over 2? Again, epsilon over 2 is also a positive number. A sub n sub k converges to a, so that difference becomes smaller than any positive number. So now I can just let things percolate through. Did we just prove that a sub n converges to a? Yeah. And maybe we'll even just check that. Only in the proof did I consider an arbitrary epsilon bigger than 0? I did. Did I then come up with a choice of big N? At some point after that, did I consider any little n bigger than big N? Did I then prove that the absolute value of a sub n minus a is less than epsilon? That's the proof convergence. Cool. How do people feel about the Cauchy criteria? That proof, I hope, felt a little bit more explicit than some of the previous stuff involving Bolzano, Weierstrass, and Linz. Today was supposed to feel a little bit lighter than previous days. Hopefully I pulled that off. Let's do an application, unless someone has any questions for us. Let's do an application. And you might even notice that the homework problems I'm going to have you do will be applications. So going through this example, I think, will be helpful for doing those applications. So let's go back to this first page. Before B prove, I think presumably that was supposed to be before we prove. Have there been any other dumb typos like that so far today? Or maybe you guys have just gotten better at reading what I meant to write instead of what I actually do write. Let's take Sn to be the sequence given by the sum from k equals 0 up to n of -1 to the k divided by 2 to the k plus 1. I claim that that sequence converges. And I'm not going to prove that it converges by computing the limit. I'm going to prove that it converges by proving that it's Cauchy. So let's do that. And just as with any other proof of limiting stuff, when you have a formula, we're going to be able to get a formula for big N, but I'm not going to have any idea what that formula is until I'm halfway done with the proof, maybe even all the way done with the proof. So hopefully this will seem familiar. Let's consider any epsilon bigger than 0, because I'm going to try to prove, well, the statement of Cauchy up there. I need to prove something is true for every epsilon bigger than 0. I need to come up with a choice of big N. I will let big N be, I don't know what goes there yet. I will now consider any little m and little n bigger than big N, because I need to consider any little m and little n bigger than big N in the definition of Cauchy. I now need to prove that a sub n minus a sub m is less than epsilon, but my sequence isn't called A, it's called S. I need to prove that S sub n minus S sub m is less than epsilon. And there's lots of steps on the next page. So I guess, let's see, would people rather this feel organic or more guided? Do you want me to go to the next page where there's steps stated? Okay, I'll go to the next page. So remember that. I'm going to analyze the difference between S sub n and S sub m. It'll be annoying that I'll have to, oh no, there, it's right there. So the absolute value of the difference between S sub n and S sub m is the sum from k equals 0 to n of that stuff minus the sum from k equals 0 to m of that same stuff. I assumed without loss of generality that little n is bigger than big M. Because one of them, let's make it bigger than or equal to. There, now I'm definitely sure I haven't lost any generality. One of them is at least as big as the other, and the definition is so symmetric it may as well be n that's bigger. So there's the difference between S sub n and S sub m. How do people feel about their analysis of series? How many people just already see some stuff that's going to cancel in that difference? How many people don't see anything that's going to cancel? Cool. Let's expand that, and we'll see something that cancels. So remember here, little n is bigger than or equal to little m. So let's expand these things out. So the sum from k equals 0 up to m of numbers that look like this, well, that's the absolute value of, or color code, this one first. -1 to the 0 over 2 to the 0 plus 1 plus, and so on. And I'm going to, in those dots, encode the first n terms. But on the way to getting to the first n terms, I'm going to hit the mth term.
But if n is greater than or equal to, then aren't you going to have two cases, one where the middle term doesn't cancel, and then you would carry those both to the bottom?
Well, I mean, if n is equal to m, that's like a super dumb case, right? Because the absolute value of the difference will be obviously 0.
Yeah.
I see the complaint that you're about to raise. You can do the dumb case if you want. So as long as little n is actually strictly bigger than m, then there's going to be some more terms in this pink bit. There will be the remaining plus -1 to the m plus 1 over 2 to the m plus 1 plus 1, all the way on to -1 to the n over 2 to the n plus 1. And that's just that part of the sum. Now I need to subtract off some other pieces. Green. Do that one in green. Minus, and I'll use parentheses, -1 to the 0 over 2 to the 0 plus 1 plus ... -1 to the m divided by 2 to the m plus 1. Now do people see some terms that will cancel in that absolute value? Yeah, the first m of them in the pink sum will cancel with all of the terms in the green sum. So let's cancel those common terms. And what are you left with? You're left with the absolute value of -1 to the m plus 1 over 2 to the m plus 1 plus 1 plus ... -1 to the n over 2 to the n plus 1. People with me so far? And I would even say in the final version I wouldn't even want to see that big thing expanded. If you need to see that to see the cancellation, great. I don't need to see that. Nice. So I say next to use the triangle inequality. Does the triangle inequality have anything to say about this? What does the triangle inequality say about an absolute value of a sum?
It says it's less than or equal to the sum of that term of the inside the sum.
Yeah, it says that the absolute value of the sum is less than or equal to the sum of the absolute values. Yeah, so that means exactly like you said, I can put the absolute values on each ingredient, and I'll make the whole thing a little bit bigger. That's not always a good idea. To do it, you might make it too big, but it'll work out okay this time. So putting the absolute values in place, absolute value of -1 to the m over 2 to the m plus 1 plus ... plus -1 to the n, need absolute values, divided by 2 to the n plus 1. Now that I put those absolute values on everything in sight, are these things going to simplify somehow? What can I do with the -1 to the n's? Do they actually make any difference now? No, they're an absolute value, so who cares? And the denominators of all of those things, are the denominators all positive? So this is going to simplify. And maybe I'm tired of writing out the whole sum. K equals m plus 1. Oop, that should be a plus 1. Up to k equals n of -1. Oh, nope, there are no negative ones anymore. 1 over 2 to the k plus 1. Nice. So I still need to show that that is very, very small. But let's just stare at it for a second. Does the plus 1 in the denominator actually have any impact when compared to that 2 to the k? Not much, so we can probably ignore it. And if we ignore it, do we make the whole thing a little bit bigger? So this in turn will be less than or equal to just the sum from k equals m plus 1 up to n of 1 over 2 to the k. Cool. I'm going to speed up a little bit because I think I have 55 seconds, possibly negative 5 seconds. So if I factor out a bunch of 1/2s, namely if I factor out 1/2 to the power m plus 1, what will I be left with? I'll be left with the sum of 1 over 2 to the k, where k is now going to run from 0 up to n minus m minus 1. Do people see what I did there? So here's what I'll suggest doing if you don't see what I did right there. Well, I guess one is remind me to go through this example starting on Friday, because I've run out of time. But check it out. This is now like 1 plus 1/2 plus 1/4 plus and so on. That's what the sum is. Now imagine you distributed this onto everything. The 1 would become 1 over 2 to the m plus 1. That's the same as the first term up here. The 1 over 2 right here would become 1 over 2 to the m plus 1 plus 1. That would become the k equals m plus 2 term up there, and so on. So, people are happy with that stuff? Well then, here's the game. There's a formula for the geometric sum, which maybe you remember, maybe you don't. How many people remember the existence of a formula for the geometric sum? Not what it is, but just if I say there's a formula for a sum that looks like that, how many people just have that idea in their memory? Okay, look it up. And crunch through for the rest of it. So I'm going to stop because at this point I'm definitely over time. Think on this example, and think on the homework examples too. If any combination of this and the homeworks from today stymie you for the next 47 hours, because that's when class happens next, we can talk about those next. Am I supposed to, did I collect homework yet? Cool. I'm going to put them right there. Oh, I should hit stop record.